Hello again, and welcome to the second part of our lecture 4 on proof basics. So in this second part, we are going to apply the concepts that we learned in part 1, so all the definitions and properties and so on, to prove a couple of simple propositions. So let's get started. Okay, so here is the first proof that we'll do, and it will be a direct proof. So the proposition says if m and n are divisible by 4, then m plus n is divisible by 4. So I strongly suggest that you now pause your video and try to do this proof on your own using pen and paper. And then you can come back to the video and see how I proved it. I think that is the best way to actually learn how to do proofs. You have to practice them on your own. Okay, so let's now try to do this together. So what are the facts we know from our hypothesis? We know that m and n are divisible by 4. So by the definition of divisibility, then we know that m. Okay, sorry, let me just set my pen in color. Okay. By the division of divisibility, we know that m is then equal to 4 times p, where p is some integer. And also n is equal to 4 times q, where q is also some integer. An important thing to note here is that we introduce two variables, p and q, since m and n are not necessarily the same. So if you use just one variable here, let's say just p in both cases, your proof would be wrong. Okay, so these are the basic facts that we can state about m and n. And then we want to prove that m plus n is divisible by 4. So let's now try to plug in these facts into m plus n. So if we do that, we get that m plus n is equal to 4 times p plus 4 times q. Great. So that is now equal to 4 times p plus q. Okay, so at this point, we can substitute p plus q with another integer s. So let's call this s. So s is equal to p plus q, and s is also an integer. How do we know this? Because integers are closed under addition. So we should make sure to write these facts that we are leveraging in our proof down. Otherwise, our proof is not going to complete. Okay, so now that we introduce the substitution, we know that m plus n is equal to 4 times s. And now, by the division of divisibility, it follows that m plus n is divisible by 4. So that follows from this visibility. So this concludes our first proof. And I think you can see kind of the basic ingredients of the proof. Okay, so let's move along now. Okay, so let's do one proof using the method called proof by contrapositive. We already learned in part 1 that if we have an implication P implies Q, then the contrapositive is not Q implies not P, and these two statements are equivalent, so we can use them interchangeably. So sometimes, instead of doing indirect proof like we did in the previous step, it's actually easier to do a proof by contrapositive. And so first we should state what the contrapositive of this proposition is. So the contrapositive of this proposition is if n plus 8 is odd, then n is odd. Okay, great. So if we prove this contrapositive, then we also proved the original proposition. So let's try to prove the contrapositive. Okay, so let's first state the facts that we know in the hypothesis, and then using that we'll try to derive the conclusion that n is odd. So we know that n plus 8 is odd, so that means that n plus 8 is equal to 2m plus 1, where m is some integer. Okay, and now using this fact we want to derive that n is also odd. So how do we do that? So if we rewrite this a little bit, we get that n is equal to 2m minus 8 plus 1. Great. And that is equal to 2 times m minus 4 plus 1. Okay, so we are getting close. So similarly to the previous proof, we are going to substitute this m minus 4 with a fresh integer. And we can do that because integers are closed under subtraction. We should write this down, the fact that we are using, so they're closed under subtraction. Let me just try to fix this a little bit. I switch colors by accident. So we can introduce a new integer s, which is equal to m minus 4, where s is some integer. And now our n is going to be equal to 2 times s plus 1. And now by the definition of odd, which we introduced in part 1 of this lecture. N is odd. And that finishes our proof by contrapositive. So by proving the contrapositive, we prove the original proposition because the two are equivalent. Okay, great. If there are things here that are not clear, please come to office hours, and I will also post a cleaner version of these scribbles on Canvas as a part of this lecture. Okay, so now after we did these two proofs, let's look at some common issues that people encounter and do when they're doing the proofs. So let's see how we will prove this proposition. The sum of any odd integer and any even integer is an odd integer. And here is one way that we could go about proving this. So, the structure looks very similar to the previous proofs. So we assume that x is odd and y is even. We have this in the hypothesis, so that's totally fine. And then we, from the definitions of odd and even, we specify x and y like this. And if you were paying attention to the first proof that I did, you might be able to notice that the creator of this proof made a big mistake here. In particular, they did not introduce a fresh variable for x and y to serve as an integer. Instead, they reuse a variable. So when you do that, you are basically assuming that this a is the same for x and y. And so you are constraining x and y to be integers that are adjacent to each other. And hence, you are not proving this theorem for any pair of integers. You're proving this theorem for two integers that are adjacent to each other. And so this is a big mistake that results in a flawed proof. So even though if you follow these steps all the way to the end, the proof will look fine, a critical mistake was made here, and that makes the whole proof flawed. So that's one common mistake. So make sure to introduce fresh variables for integers that are not related to each other. Okay. So let's do here now a corrected proof of this proposition. So, okay, so we're going to prove that the sum of any odd integer and any even integer is an odd integer. So let's introduce an odd integer. X is equal to 2m plus 1, where m is an integer. M is some integer. And y is any even integer. So y is 2n, where n is an element of z. Wonderful. And then we want to prove that their sum, that x plus y is odd. So x plus y is going to be then equal to 2m plus 1 plus 2n. So that is equal to let's group these things a little bit differently because we want to get into the form that tells us that x plus y is odd. So we have 2m plus 2n plus 1, which is equal to 2 which multiplies m plus n plus 1. And now we do the trick of introducing a fresh integer that replaces m plus n by substitution. So we get 2 times s plus 1. And we can do that where s is equal to m plus n and s is an element of z by closure of addition. Let me write this on the side, closure. Don't forget to denote why we can actually introduce s here. Okay, now by the definition of odd numbers, we know that x plus y is odd. And this is the corrected proof of this proposition. Okay, wonderful. So we did 3 proofs so far. I hope you're trying these proofs on your own. Like I said, that's the best way to practice. So after you see the proposition, pause the video and first try to do the proof on your own before you follow along with what I've been doing. So some observations here. We already covered this in part 1, but I want to repeat them because I think they're important. So, when you're starting your proof, use the definitions to express things that reveal fundamental properties about your hypothesis. So use variables that present any element in the domain, such as integers. And do not use the same variable to represent 2 different things. We saw that problem with that float proof. Also apply rules and then properties that are true for every element in the domain. So based on that, reach conclusions that are also true for element in the domain. And that's how you do your proofs. Okay, let's look at another problematic proof. So proposition 1 to prove is that for all integers, if n squared is even, then n is even. And take a look at this proof and pause the video and maybe think a few minutes about it and see if you can spot a mistake. So let's follow the steps of the proof and see if we can see where the mistake is happening. So, okay, we start by specifying that n squared is even, which we have in our hypothesis, by following the definition of even. So that looks all fine. Okay, and then in the next steps, the author of this proof divided both sides by n. And this should raise a red flag right away. So what is the problem here of dividing both sides by n? So the problem is that, as we learned, integers are not closed under division. And so once you divide something by n, what you get might not be an integer anymore. And so in the next step, the author replaced this division of k and n by introducing this new integer m. However, this m is potentially not an integer. And this breaks the proof. So the message here is that you have to be careful that whatever operations you perform are closed on the integers. And division is not one of them. Division is not one of them. Okay. Let's give this proof another try. So we have the same proposition. And then let's prove the converse of it. So we want to prove the converse, which states that if n is even, then n squared is even as well. And take a look at this proof. and see if you can spot the problem with it. Maybe spend a couple of minutes here. Okay, so now what is the problem here? Let's look at the proof. So we have n is even. Based on the definition of even, we can write that n is equal to 2 times k. We square both sides. N squared is equal to 4k squared. This all seems fine. Multiplication is integers are closed under multiplication. We factor out 2. So we have 4k squared is equal to 2 times 2k squared. By closure of integers under multiplication, we have that n squared is equal to 2 times n, and with addition of even, n squared is even. So this actually looks all good. So what is the problem with this proof? Well, the author made a mistake early on by actually proving the converse of this proposition. So note that converse of an implication is not equivalent to the implication itself. Contrapositive is the one that is equivalent. So therefore, we can do proof by contrapositive, but we cannot do proof by converse. So this is just a wrong indirect proof, and the mistake was made here when we were doing this indirect proof by trying to prove the converse. So be careful there. The contrapositive is the only one you can do. Okay, so I'm not going to do the corrected proof with you. I think that we did a couple of now proofs that are very similar to this one, and then you should be able to do it now on your own at home. As a hint, use the proof by contrapositive method and prove the contrapositive statement of this proposition instead of this proposition directly. So that should allow for an easier proof. And if you get stuck doing this, please come to office hours. This should actually be a fairly easy proof to do. So one important thing when doing proofs is that you carefully specify all of your steps and make sure that your notes and your solution is organized. So don't scribble all over the place. Have clear sequence of steps that we can follow easily when we're grading. And when you're doing things like substitution and so on, note that, for example, integers are closed under addition and things like that. So note which definitions and properties you are using in your proof. So that will help us and to grade your proofs properly and for you to get all the points. Okay, another type of proof that we'll do in this class is proof by cases. So again, I already mentioned this proof in part 1. Now we'll actually put that into action. So sometimes it's kind of really hard or even impossible to prove something for all possibilities at once. And so then a good idea is to partition the possibilities into a finite number of cases and prove each one of them individually. You of course have to make sure that the cases are exhaustive and that they indeed cover all the possibilities. So here is one proposition where proof by cases is a natural and easy way to do it. So the proposition says if n is an integer, then m that is equal to n squared plus n is even. So what are the possible cases here for n? And this is a very common situation where we use proof by cases. Well, we know that all integers are either even or odd. We have a theorem about that. And so these are the two cases that we'll look at. So let's try to do this proof. So we have our proposition and our case 1. Is when n is even. Okay, so what do we know then? by the definition from even, we know that n is in that case equal to 2 times m, where m is some integer. Let me write this again. Okay. Oh, yeah. You see, I made an interesting mistake here. So this is a good example. When you're introducing these new variables, these new symbols, don't introduce something that you already have in the proposition, because that is going to be really confusing. So we already have m here in the proposition, and I should actually use a different, introduce a different symbol here. So let me erase this. Instead of m, you can pick any letter you want. Let's do p, 2 times p, where p is an element of z. So this will help us to avoid confusion. This was a good example of a common error you can do in proofs. Great. And now let's plug this into m. So we have m is equal to n squared plus n, and that's equal to 2p squared plus 2p. That's equal to 4p squared plus 2p. Okay, what do we do next? Well, we want to show that that is even. So we want to leverage the definition of even numbers. And we want to try to get this into that format. So we pull out 2, and in the parentheses we have 2p squared plus p. Okay, we're almost there. Now we can substitute 2p squared plus p with q, where q is an integer. And we can do that because of closure properties of these operations. Wonderful. So once we do that, we get that m is equal to 2 times q. And by the definition of even, that means that m is even. So that proves our case 1, where we proved that when n is even, m is also even. Now we still have to do case 2. Which is the case when n is odd. Okay, so please pause your video now and try to do this case 2 on your own, and then come back and we'll do it together. And it's really similar to case 1. So, okay, so let's do it. So what do we know? We know that n is odd, which means that n is equal to 2 times q plus 1. Know that you can well, let's actually use p, the same as in the previous case. In the case of proof by cases, you can reuse variables across cases because each cases are independent. So n is equal to 2p plus 1, where p is an integer. So then we plug this into m. So m is going to be equal to 2p plus 1 squared plus 2p plus 1. Okay, so we'll have to expand this now. So remember how you do square of parentheses. So we have 4p squared plus 4p plus 1 plus 2p plus 1. That is equal to, so let's group this together a little bit. We have 4p squared plus 6p plus 2. So the same as before, we want to prove that this is even, and we want to use the definition of even integers. And so let's get this into the appropriate form. We pull 2 out, and we get 2p squared plus 3p plus 1. Okay, now we can substitute this whole parenthesis with a fresh integer. Let's call it q. So 2p squared plus 3p plus 1 is equal to q, where q is an element of z. And we can do this because multiplication and addition are closed under integers. So closure. And once we do that, we get that m is equal to 2 times q. And from definition of even, we know that m is even. And so this concludes the proof of our second case. And so in the first case, we proved that this holds for even integers, in the second for odd, and therefore we can conclude that the proposition holds for all integers, because every integer is either even or odd. So that's an example of proof by cases. Okay. So this was it in terms of lecture 4. So try to do proofs on your own. We'll do more proofs on Tuesday and Thursday during the recitation and discussion sections. I have to warn you that many students in CS2100 struggle with proofs and they find them particularly hard. And so make sure to practice proofs a lot. And if you struggle, please make sure to come to office hours. There are many office hours led by TAs and some by professors, and you can come to any of these if you get stuck on proving something. Thank you for watching, and I'll see you all on Tuesday.